Next, I'd like to talk about the mathematical terms rational and irrational. And the word rational comes from the word ratio. So, rational, root word is ratio. And what is a ratio? Well, we think of ratios as fractions. And a ratio can be a fraction of a decimal number or a decimal number, but in the context of rational numbers, a rational number is a ratio of integers. In other words, it's a fraction with, a conventional fraction with integers, top and bottom. Okay, well, all numbers that can be written as rational form a large collection of numbers, the rational numbers. And of course, they not only include fractions, they also include the integers, because any integer can be put over the number 1, and so it too is a ratio, a rational number. So rational numbers are what we first learn about. You first learn how to count, and then later you learn how to divide things up into parts. And when you divide things into pieces, you create rational numbers. So now, rational numbers are associated with patterns. Now, when I was growing up in the 60s, when I was young, nobody had electronic calculators. We had to do all arithmetic by hand. And so to me, math was pattern. Mathematics was nothing but patterns. And I saw that in about everything I did in math, particularly when it came to division. When you divide numbers, you create a pattern. So for example, the common one is 1/3 is 3 divides into 1, and what happens? We get a string of 3's, which repeats endlessly because the long division repeats the same pattern over and over again. So there's a pattern, a very simple pattern most people are familiar with. Here's one I kind of like. Let me see, it is 41 over 333. And if you divide that out, you're going to get 0.123123, and it just repeats on and on and on. So there's another nice pattern there. I kind of like this number. I call it the Lawrence Welk number. And for those of you who are too young to know about Lawrence Welk, he was a TV personality who had a variety show, and his band played a lot of waltzes. Waltzes are in 3 time. 1, 2, 3, 1, 2, 3, 1, 2, 3. So to me, this is the Lawrence Welk number. All right. Anyway, another pattern which exists. It turns out it can be shown that anytime any rational number is going to create a pattern in the decimals which repeats endlessly. And that pattern is called the repetend. So every rational number has a repetend, which is it's the decimal part which repeats endlessly without any change. So here the repetend is 1, 2, 3. Up here the repetend is just a single digit 1. Alright, well, it's an interesting question to ask. Can you predict the size of a repetend of certain rational numbers? One of my favorites is this number. And if we had, lots of time in this course, I could show you that the repetend of this number is 50 digits long. Without physically dividing it out and verifying it, you can show that this thing in decimals must repeat 50 times. All right. Wish I had time for that. Okay, well, hopefully I made my point that fractions or rational numbers in decimal form have a repeating pattern. All of them do, and that can be proven. So, what about numbers which do not have a repeating pattern? And here's one we can construct. This actually is credited to Georg Cantor, who was a very interesting mathematician, lived in the latter half of the 19th century. If we take this number and then tack on 0, 1 and 0, 0, 1 and 0, 0, 0, 1 and continue that, it has a pattern that's identifiable, because we can, from this, we can glean a pattern from which we can continue to tack on more ones and zeros, but there is no repetend. There's no part which repeats. And so this number, if you continue that pattern without the repetend, it's not a repeating decimal in terms of rational numbers. So it doesn't fit that working definition of rational number. And it turns out this is a number which cannot be represented by a fraction. All right, in another video I'm going to show you that the square root of 2 is such a number that cannot be represented by a fraction. And it's I hope you watch that video and take note from it. I think it's a fascinating discussion. All right, so let me cut to the chase on all this. An irrational number is a number which does not have this repetend or consistently repeating pattern of a fixed amount of digits. And so, for example, the number pi is approximately 3.1415962, and it goes on and on and on and on and on. And there is no pattern, recognizable pattern to these digits. In fact, pi has been calculated to several hundred billion decimal places. You might wonder, why in the world would eBay be interested? It's not interesting, except for one purpose. When people build a very expensive supercomputer, and these are huge machines, these are machines which are very powerful. They usually cost in the tens of millions of dollars. When these big supercomputers are built, one way they can determine if it's working properly is to have it calculate pi to many millions or billions of decimal places. And what they do is that they just compare that result with another computer's result, and they figure out that if they agree after all those decimal places, then those computers must be working properly. So that's the thought there. There are there are far more irrational numbers than rational numbers. And in fact, if you took a number line and threw a dart at it, if the number line represents a continuum of numbers with no breaks in them, if you just threw a dart at the number line, there's a 100% chance that you're going to hit an irrational number. There's effectively a 0% chance of hitting a rational number. That's how many more irrational numbers there are from rational numbers. So that too is a long story. I like to tell you these little tidbits to hopefully tantalize some of you into believing, as I do, that math is a very fascinating subject. All right, so the square root of 2 is an irrational number, and it's approximately 1.4142135, and I forgot what goes after it, but it goes on and on and on and on also. And I'd like to show you, give you a glimpse of how to calculate a square root. But before that, let me kind of wrap up the real point of this video clip, is that when you take the radical of an integer, whether it be square root, cube root, seventh root, any root you want to, when you take the radical of an integer, if it's not an integer itself, then the number is irrational. It cannot be written as a fraction, and its decimal form has no constant repetition, as you find in rational numbers. That's the difference there. So, but I know some of you are interested in how can you calculate this without a calculator. Well, I learned this in 7th grade. That was before there were calculators. And boy, was it a revelation for me. So I'm going to show you how to calculate the square root of 2. There are several ways to do this. One involves calculus that uses a method developed by Sir Isaac Newton. There's a way of calculating other kinds of radicals, named after two obscure Southwest Ohio mathematicians, the Davidson-Carver method, or it's the Carver-Davidson method, depending on who's teaching calculus that year. And there's some other methods involving some kind of guesswork with it. But here's what I learned. And so, in case you've always wondered, how can one calculate a square root? So, the square root of 2. And I'll only go to a couple places and you'll get the idea. So there's 2. I'm going to put my decimal up there. Whoops, that's not correct. Alright, so what perfect squared number divides into 2? Well, 1 does. So I'll put a 1 up here, and 1 times 1 is 1, and I subtract, and I get a 1. And now, instead of bringing down the next digit as you do in conventional long division, I'm going to bring down the next 2 digits, which in this case are zeros. Yeah, I really don't need this line yet. Alright, so subtracted 1, brought it down, brought down the next 2 digits. Now what I'm going to do here is I'm going to double the last digit I got. That makes it a 2. And then I need to put a number here. And the number I'm going to put there is 4, because 4 times 24 is 96. It's the largest number I can put here, such that this number times that number is still less than that number. Alright, I hope that made sense. But after you see a few of these, I think you'll clearly have the idea. So I subtract. That gives me a 4. And I bring down the next 2 decimal places. And then I double the last digit. So that 4 becomes an 8. I have 2 8. And then I create a new digit. So I have 280 something divides into 400. I would have to use a 1 here. 281. So 1 times 281 is 281. Subtract 119. Bring down the next decimals. Double the last digit. 282. Create a new space. And now I have to think about 2,820 something divides into 11,900 4 times. So I'll put a 4 up here. I'll multiply that out and subtract it. See, 96, 112. And I think probably you're hopefully getting the idea here. Bring down another set of zeros. Double that digit, so forth. Alright, so that's the idea. And that method can be used to calculate square roots. And so at one time people needed to know how to do that. Because if you needed a square root, and you had no calculator, you either had to calculate it yourself, or you had to find a table with those values listed in them. So these things we had to do manually at one point. I got real excited when I learned about this in 7th grade because, again, to me math was pattern, and I had never heard of a number not having a decimal pattern. I thought, wow, that was amazing. And my teacher said, look, if you continue to do this, you'll never see a pattern. So, wow. So I went home and I saw for myself. I did this out to 23 decimal places. I had to write very small on the largest piece of paper I could find. That's as far as I could go. And after 23 decimal places, I was pretty convinced there was never going to be a pattern. And it was never going to end. So that was my introduction to irrational numbers.